topics related to the support vector machine. First, I want to say a few more things about different kernels that people have constructed, going into detail regarding one of those kernels. I will then introduce two variants of support vector machine, discuss one of them in detail, namely a method that's useful for outlier detection, and discuss a second method, just very, very briefly, and leave it at that. And we'll then take you to decision trees and ensembles of decision trees. Those are very powerful, but not so much beloved by textbook authors, it seems, because they don't have a native probabilistic interpretation, but they fare very well, so it's worth knowing about these. Okay. So kernels for structured input first. There is a general framework, namely convolution kernels, which has been proposed by Hauser. And that works in many settings, but I want to give a few concrete examples. So one that does not fall under convolution kernels is a so-called Fisher kernel. It allows you, in particular, to compare data sets of different size. So let's say you have an audio signal. Let's take amplitude and time. So you have some audio signal of somebody saying something to a mechanical operator. And then you have another audio signal by somebody else saying something to the mechanical operator. And you know this when you call somewhere and they want to know, do you want to open an account or do you want to enter your existing account? And then they ask you to enter numbers and so on, or speak numbers into the phone. And different people speak differently. And let's say that we want to understand if somebody said yes or no. Now, unfortunately, these signals have different length. So the first signal ends here and the second signal ends there. So we need to somehow map them, or we want to somehow compute the similarity between these two signals of differing length. And the proposal here for the Fisher kernel is to consider a generative model and then take the derivative of this generative model with respect to one or the other input and use those derivatives to obtain a kernel in the end. So in particular for time series like this, you could use as a model a hidden Markov model. We will discuss these at the end of the semester. So for our purposes, a hidden Markov model is I meant to use a generative model, sorry. This is just a model parameterized by a vector of parameters, theta. And such a model can generate sequences of differing length. And one can now compute the gradient of the log likelihood. So we take the gradient with respect to the parameters So x are our observations here, which can be of time series, for instance, of different length. Theta are the parameters. And we now take the derivative of the log likelihood of a given model, the log likelihood of the data given a certain parameter. And Fisher kernel can then be defined as follows. Where I is the Fisher information matrix. So it's the expectation with respect to our observations for a given parameterization of the outer product of ux transpose. So in essence, what you do is you ask in which way would the parameters theta have to change to explain this time series better, or how would the parameters need to change to explain that time series better. And if these two different time series pull the parameters in the same direction, then you obtain a large similarity, a large value for your kernel. And if they pull in orthogonal directions, then you would say these are very different, and you would get 0 kernel here. Then there are kernels for graphs. To be more precise, there are, on the one hand, methods that look at nodes connected by vertices. And there are some methods which consider each node of the graph as a separate observation. And so when you compute a kernel between two nodes, you want to know, well, how similar are these two nodes to each other? And a popular kernel here is, for instance, based on diffusion, where you can specify an amount of time. This would be a generalization of the Gauss kernel or the RBF kernel to graphs. So if you start, let's say, with all your probability mass here, and then you can diffuse over a single time step or over more time steps, and you essentially get, well, you solve the heat equation, so you get a spread of this probability mass across your graph. And if you cut off this diffusion process at a given instance, then you can check how much of the probability mass from the starting point has arrived at that other point, and that would be a measure of similarity. And this can be related to random walks and so on. So essentially you compute by how many ways two nodes are connected. But there are also other graph kernels where you really compute the similarities of graphs themselves. This is related to the graph edit distance. So you could want to compute not the similarity between two nodes in a graph, but between two graphs, really. And different methods have been proposed for that. And then there are kernels driven by syntax. So for instance, bag of words kernels are used for strings, or dynamic time warping can be used. And there is one that I now want to discuss in more detail, namely the Optimum Matching kernel. This this is work from Kristen Grauman and Darrell. So Kristen Grauman is a young scientist, and I like her papers. They're very clear, I think, and she often has nice ideas. So it's a good idea to follow her work. Now, the aim of these pyramid matching kernels is to find a similarity between two sets of objects that are each, with each of these objects being embedded in a feature space. In particular, the two objects can be of different, or the two sets can be of different size. So the pyramid matching kernel is sometimes abbreviated compute some kind of similarity between two sets of objects, and all of these objects lie in some feature space of dimensionality P. So one nice thing about her paper is that, in my opinion, she summarizes the message of her papers really well in just a few figures. And in this case, the task is to compare two images, so a mug and an apple or pear in this case. And, well, the task is to compare these objects. So with a little less light, you will see that there are a couple of points that have been marked. So some interest points have been found. And each of these interest points is characterized by some features. So we have an independent procedure that finds, for instance, corners or generally interesting points. And then each of these points is characterized by some features. So in this sketch here, each interest point would be characterized by just two features, but in reality, it will be many more. And you can now do that for a large number of objects, and you then want to compare the interest points that you found in one image with the interest points that you found in another image to decide if these images may be of the same class or not. So down here is a schematic picture of this comparison process. We have this feature space represented at multiple resolutions. We have this set of features represented at multiple resolutions. And one would like to compute an optimum match between the two sets of points. And this optimum match can be approximated by an intersection of these two multi-resolution representations. So the exact problem to be solved would be to consider two sets of points. A and B, with each point being embedded in p-dimensional space. And let's say that the set A has a cardinality m. We have m points, and we have n points in set number B, with the first set being larger than the second, larger than or equal to the second. We also need a permutation. And the cost of a partial matching is then given by assigning each member of the smaller set to some member in the larger set, with no 2 points being allowed to map to the same point from the other set. So the matching is partial because one set of points may be larger than the other. Okay, so we have a sum over all members of the first set, and we compute the sum of the absolute differences between those members and their assigned members from the other set. So we have B sub pi sub I. Pi is the permutation, and I is, well, the ith element of that permutation. So this permutation encodes the assignment between the two sets A and B. And because we want to work with kernels, we want to have similarities rather than costs or differences. So one can compute a similarity instead of a given matching and well, if we had just this functional form, we would have a similarity that goes to infinity when the two elements are identical. So for regularization, a constant is added here. Okay, then the optimum matching is given by the permutation pi, which minimizes this overall cost. And finding the globally optimum permutation is an expensive operation. So dimensionality times the kernelity of the larger set to the third power. So this is standard, nothing smart done so far. And now comes the proposal, namely to use a feature extraction function instead, a pyramid of histograms, and to then approximate the true similarity by intersections between these two histograms. So in this case, this is a schematic summary of everything that I will say in the following. We have, in this particular case, a 1D feature space with a blue set and a red set of points. And this one-dimensional feature space is now represented, or the objects are represented by histograms of varying resolution. So here we have a very high resolution histogram, and you can see, so here are the bins, and these are the counts. So we have a red and a blue histogram at very fine resolution, and then the same thing at a coarser resolution and at an even coarser resolution. You see that for very high resolutions, these histograms are sparse, so they have mostly 0 or 1 entries. And then as we make the histogram coarse, we find, for instance, here up to 3 observations in a single bin. Okay, now the argument is that the similarity between these two histograms is given by the intersection of the two histograms. So intersection being defined as take in each bin the minimum value of the number of counts that you find in both histograms. So you see, let's take this coarse example here. We have a blue count, but nothing in the red histogram, so we get a 0. We have 2 blue counts, but only 1 red, so we take the minimum, we have a 1, and so on. Okay, and already graphically, you can see that, well, at the coarse resolution, we have much higher intersection or much higher similarity than at the very fine resolution. And, well, that is natural. So if you take a very coarse histogram, you know, if you just take a single bin, then yes, both of your data sets will be perfectly similar. If you take extremely fine bins, extremely highly resolved histograms, then your 2 objects, the blue and the red one, will, with very high probability, be totally dissimilar. So the intersection will be empty. And somewhere between these 2 extremes, the similarity of 2 histograms is actually encoded. And the idea here is to do this encoding efficiently. So the proposal is we want to find a cheaper alternative as follows. By first defining a feature extraction function. A pyramid of histograms. So this pyramid of histograms of a set A would be defined as the histogram at level 0 of our set A, and then histograms at increasingly finer resolution up to a histogram at level L minus 1. So this would be the histogram at level 0, which in this case is here defined as the highest resolution. And this would be the histogram at the coarsest resolution. Now, there are different ways of partitioning your feature space. In this original paper, the suggestion was the following. So the suggestion was, I'm drawing here a 2D feature space instead of the 1D example that you have previously seen. So the original suggestion was to use boxes, with each of these boxes being partitioned at increasing levels of detail. So in this case, we would have level 0 in pink, and then level 1 in green. but there are many other ways of partitioning feature space. And in fact, in a later paper, they used a hierarchical k-means tree to partition space in ways that are better adjusted to the distribution of the data. So for this particular example here, psi of A would be, so I'm not giving, so let's say we have a set A of points in this feature space. And we would now have a histogram first at the finest level. So we have what? So we would have 64 bins at this finest level, and then 32. So 64 bins for the first level, and then we would have 32. No, even less, huh? So we start at so we would have 64 and then 16 bins and then 4 bins, with each bin holding the number of counts that fall into a particular bin in this data set. And now the suggestion is to approximate the similarity as follows. And this is called the pyramid match. So the delta means that it's a measure of similarity or dissimilarity. P supposedly, probably stands for pyramid, and this pyramid match between the feature extraction function between a set A and a set B is given by a weighted sum over the newly matched pairs at each level. So let's look at these terms, and this is simply defined that way. Let's look at these terms in more detail. So Ni are only those points that now lie in the same bin at a higher level, or at the coarser level, but not at a finer level. So capital I now is not the indicator function, but here it's the intersection function. So this is what's happening at level I, and we're subtracting all those intersections that were already found at the previous level. And the intersection function itself what's written here, intersection function itself. Okay, I'm writing again to omit the index of the resolution that we're looking at. So R is the number of bins that we have in each of the histograms. So we're summing over the minimum of the respective entries in the histogram. So this would be here the count of objects of type B in the jth bin of this particular histogram. Now the weights are useful in the following sense. If we go to a sufficiently high level, to a sufficiently coarse level, we will always have lots of intersections, but they're not so meaningful. So we want to attach more importance to matches or intersections that are found at high resolutions. And this is captured by W. So Wi is a weight function that gives higher weight to matches that are found in those histograms with very many bins. And for this particular setting here, the authors have considered the L1 distance between points and have then argued, what is the greatest possible distance that 2 points can have. And they then come to suggest a weight function that is just 1 over the largest possible distance between any 2 points within a bin. Now, as it stands, this formula would have a bias towards comparisons with larger sets. So if you compare A to B and C, and C is much larger than B, you would also find more intersections. And hence, the authors propose the normalized pyramid match. So to avoid bias favoring large sets, you can use the normalized pyramid match. Which is defined in terms of the unnormalized one as follows. Now the idea was to use this as a kernel, so we should check about Mercer's condition. So we want to know if this is always positive semi-definite, or we want to know if we can rewrite this kernel as inner product of two vectors in some high-dimensional space. And indeed, it is fulfilled, and I like the argument that's used to show that it is fulfilled. So you see that the pyramid match, the unnormalized one, is a combination of newly matched pairs. So this can be rewritten as follows. So you see that we have a linear combination here of intersections, and Mercer's condition will be fulfilled if the intersection itself is a Mercer kernel and if this is larger than or equal to 0. And intersection is indeed a Mercer kernel, which can be seen as follows. So consider we want to use some mapping to a high-dimensional space. And we can represent an R-bin histogram. So a histogram with R-bins in which a total of m points reside. By a binary vector of dimensions r by m. As follows. So phi is the high dimensional mapping of our histogram. And this can now be written, for instance, let's say that we have 2 counts in the first bin, and then we have a total of m minus 1's 0 left in that first bin. And taken all together, these would be R elements. Sorry, M elements. So we have our histogram has that many counts in its bin 1, and we can write so many ones, followed by the corresponding number of zeros. So for each element that has fallen into this bin, we put 1, 1, and fill up the rest of these m indicator variables with zeros. Okay, and this whole thing is repeated up to the last bin, bin number R, where we, let's assume we had perhaps a count of 4. So this would be H of R ones, followed by that many zeros. So essentially, we represent the histogram by an indicator vector. And now intersection was defined as the sum over the minimum elements. And if you think about it for a moment, you will see that this intersection is indeed given by the inner product of two such vectors, because you only get a contribution to the inner product when you have a 1 in both vectors. So intersection between two histograms is given by the inner product of such indicator vectors. And because we can write it as an inner product in this high dimensional space, this means that it is a Mercer kernel. So summing all of this up, well, the formula I had already written there. So we have overall some similarity measure that we can show is a Mercer kernel. And also in the paper are a couple of arguments why it's actually a good approximation to the exact similarity match that go beyond the intuition that the sketch has hopefully conveyed. And this whole thing can be computed highly efficiently. So if you use this particular representation here, then the cost that you pay if you use a single of these multi-resolution histograms would be P times N times L. So L would be the number of resolutions, number of levels. M is the number of points in the larger set, and P is the dimensionality. And this is the cost that you will pay both for the construction of these of this representation and for evaluation of the cost of a matching, rather than the order m to the 3 that you would pay for the exact solution. Now, there are a couple of technicalities, in particular using such a single multi-resolution histogram that can introduce artifacts. So the similarity between two sets of points, so let's have the white set of points and the yellow set of points. So the similarity that you will get will depend on where exactly you put the starting point of your histogram. So let's say that the origin of the coordinate space is here. But if you now shift this histogram a tiny little bit, you will empirically get out a different number for your pyramid match. And well, these are artifacts that you don't really want. So one suggestion is to use multiple such histograms that are both shifted a little bit, and in particular it's important in high dimensions that are also oriented at some random fashion. And that will give you more stable similarities. Instead, you see in this example here, most bins are 0. Instead, you can, as I mentioned briefly, construct different multi-resolution histograms, for instance, by using the hierarchical k-means tree. We will talk about k-means later in the semester, but roughly what you do is the following. If you have a cloud of points, you may, for instance, first, if you use 2 cluster centers at a time, you might find that you have one cluster center here and one cluster center there. So your initial partition of the space would be this one. And now you can recursively partition each of the clusters. So for instance, you would find in the next recursion that this white point, if you replace it by 2 cluster centers, would partition the remaining data like that. And if you put 2 cluster centers here, you might put them at this position. And you can thus recursively partition space in a way that is better adapted to the distribution of your data. And well, these authors, they don't call it the hierarchical k-means tree. They call this, when they use it in this setting, a vocabulary guided pyramid match. Okay. Any questions for now? Then we will have a 15-minute break.